Today I'm talking with Yannick Ulrich, who's one of our physicists here at the IPPP in Durham, about his career in physics and his research. Hello, Yannick.
Hello, Fran. Thanks for having me.
So the first thing I wanted to ask is, what would you say the one big question that your research is trying to answer is?
So we have this theory of essentially the universe, which is really good for the things where it works, but we know it's not complete. There are various things that we know it's incorrect for, and we want to find out how to extend it to work everywhere. And now the problem is, like, there are experiments at CERN or elsewhere that look into this, that try to measure physics beyond this theory, and that take data. But at some point, someone has to look at this data and try to deduce what type of physics this implements. And to do this, you need to understand the theory that you have really well. And this is what I do. We try to understand the theory as good as possible, trying to get as good a prediction as possible for the things that we try to measure, so that if at some point someone compares that to data, they're going to be able to get the best possible result and not be limited by the theory uncertainties. And so this is essentially what I do. We try to, the question is, if you want, how do we make the most out of the data? How do we get the best theory prediction for this data?
So you're trying to predict the results of measurement very, very precisely, is that right?
Yes. We try to predict it for the bit that we understand. There are other bits that we don't understand or that we want to measure for some reason. And this is obviously not what we predict, because if we were able to predict it, we wouldn't have to measure that bit. So we try to predict the thing that we know to be true. And then whatever the difference between that and the measured data is, that's the physics that we try to measure.
So maybe we could think about it for an example.
Sure.
What's your most recent calculation?
So one thing we look at is scattering process. So you take particles called muons. They're sort of like electrons, but just a bit heavier. And you actually shoot them on electrons. And if you do that, you are sensitive to a certain process that we know exists, but that we can't calculate for reasons of physics that are very complicated to explain. And we try to measure this. But to do that, we need to understand all the bits that we can calculate, because there's one bit, one type of diagram that we can't calculate. And so we try to measure this by first calculating all the bits that we can calculate. And the difference between data and the calculation is then the bit that we can't calculate.
Right. So is the idea that we have the standard model of particle physics, which predicts things very, very well. But actually, there's some things that are very mathematically difficult to predict from the standard model. Even though we understand the model, you have to do some very difficult calculations to predict things to high precision from that model.
Exactly.
And you're in charge of some of those calculations.
Yes.
Great. So the next question is, why did you decide to become a physicist?
So I actually had to think about this quite a bit because it's quite a while ago. But so in school, at some point, we were asked what type of work placement we want to do, and out of the blue, as far as I recall, I decided I want to at least try to get a work placement at the National Lab for Physics that's near where I live in Germany, where my school was. And I just, out of the blue, decided, yeah, let's try that. And it actually did work. So then I must have been 12 or 13 years old. Went there and had a fantastic time and decided that this is what I want to do. This was supported by me having a fantastic physics teacher who sort of supported that and tried to guide this along and tried to help me get along there.
Nice. And okay, bonus question. Have there been points in your physics career where you've had second thoughts about that decision?
Not really. There might have been, like, at times I thought maybe I could have gotten to this to a point where I am now, or something socially equivalent, through an easier or more efficient route where I would have learned more things that were helpful for me. But I never really thought not becoming a physicist. And I still don't. I still absolutely love it.
Okay, so moving on from that, what is your favorite physics fact?
Right. So it's slightly technical. So I'll try to explain it. It's called Noether's theorem. And the idea is that if you look at the world or any theory of physics that you have, if that is symmetric in some way, for example, if you look at the world, it doesn't matter where you look if the world's empty. So if you look this way or this way, it doesn't matter. The rules of physics don't change if the world's empty. And that implies through these theorems, through Noether's theorem, that there are certain quantities, certain things that are conserved. So the amount of spin something has, so the amount of rotational momentum it has, is conserved because it doesn't matter in which direction of the universe you look into. And this conservation of angular momentum is something you see, for example, through ice skating. This is the example people usually bring up for this context, that if the ice skater spins and then pulls in their arms, they start to speed up, start spinning faster. And fundamentally, this is because in an empty universe, it doesn't matter which direction you look into. And there are other things like that. So for example, if you move in time, that means, because there's no universal time, it means energy is conserved and stuff like this. And I find this incredibly fascinating, this deep underlying reason why that is the case, and that you can prove that mathematically.
Yeah, nice choice. I think the time example is a good one.
Oh,
I think many people watching might have learned about conservation of energy at school. Energy can't be created or destroyed. It's always conserved. And this turns out to be a consequence of the fact that the laws of physics don't change with time. And that's pretty cool. And it's possible to prove that mathematically. So what physics discovery do you most hope to see in your lifetime?
So something I always find interesting are particles called axions. They're one of these extensions for the standard model that we mentioned earlier, and they solve many problems in one go. And this is actually why they're called axions. Axion is a brand of I think cleaning detergent in the US, and the guy who invented that just named it axion because it solves so many problems in one sweep. And I would love to see those discovered experimentally confirmed, because it would solve many problems in one go and provide us with new insight and how to continue from there.
So you've spoken about how you're in charge of doing some calculations that will enable us to predict particle properties more precisely. So what does this involve day to day? Can you describe a typical day in your job?
Yeah, so one of the reasons I love this job is because there are many roles that I have to fill. So some days are mostly like software development, where I have a bit of an objective that just needs to be transformed into code, which is relatively normal down to software development. Other days are spent teaching undergraduates or supervising students. And then again, some days require like algebraic manipulations by hand or with the computer, and writing down, trying to solve big equations with the computer, or trying to work out how to do these things by hand on a piece of paper. So there's no really one typical day that covers everything. So all these things come and go depending on what stage of the project I am. There might be conceptual things which you do on a piece of paper, or they're just coding things when you know when you work out all the conceptual problems and have to just put it into code and try to see where that actually works. So it's difficult to say that there's this one thing that this one typical day.
Yeah.
And this is why I like this type of work.
Yeah, that's great. I think I certainly find the same, that some days are conceptual and other days you have to, go and sort out all the details of the thoughts that you've had. And outside of physics, what are your hobbies and interests? What do you do when your physics day is over?
So I really like reading and just generic novels or whatever. I have a sort of very amateurish interest in Greek mythology and linguistics,
Cool.
which are totally separate things and have nothing to do with physics. I just find these things fascinating, but this is very amateurish. I don't do that now because of lockdown, but in my previous life before lockdown, I played the violin in an amateur orchestra.
Yeah. Okay. So thank you very much for talking with me, and I hope this has given people a flavour of the kinds of things we do at the IPPP and what that looks like on a day-to-day basis.